Hello, physics kids. Mr. Johansson here. Today we want to talk about electric current. All right, electric current. Here's a device that shows the direction of electric current flowing through it. I have it hooked to a power source, and this is showing how electricity is flowing through it. In order to do that, we need some conventions, some schematic symbols that are used. In other words, drawings of electric currents. This would be a resistor, the line back and forth like that, and this would be a power source. So in order for electric current to flow, if you think about the Van de Graaff generator, it's filled with electrons there. If I connect it to the ground, those electrons will pour out of it and dump into the ground. Along the way, they'll do work on whatever is allowing them to go to the ground. In other words, they'll heat up the wire. But as soon as I connect that wire, all those electrons drain out, and the Van de Graaff generator is basically empty. Would need to fill up again. So it could do work in pulses. Well, that's not really useful. Long time ago, people developed batteries. Batteries can do work like this, a battery connected to a little light bulb. I don't know, can you tell that the light bulb is actually on there? Yeah, well, the light bulb is on. The battery is pushing electrons. The electrons going through the filament here, the filament doesn't allow them to go through so easily. The wires let them pass very easily. But the filament holds them back. It makes them push pretty hard to go through, and all that pushing that they have to do makes heat, makes a lot of heat. So much heat that the filament glows brightly. That's how all incandescent bulbs work. So that is a fundamental idea of electric current. We need something to pump electrons up to a state where they're pushing against each other and they'd like to get out. In a battery, the chemical reaction does that. And then you need to connect them to something that will resist their flow. And then you need to bring them back down to the other side of the battery. So electric current, it has to be in a closed loop in order to function. Let me draw that for you. Okay, so if we had a power source, like a battery or plugged into the wall, and we have some resistor, and it has to come back. If I interrupt this anywhere, any place, if I make a break in the wire, it shuts down the entire current everywhere. There's no place else in the wire where there's still current. You open that and the wire is open. It's not allowing electrons to pass. The only reason the electrons are coming into or out of the battery, the only reason is that there is some pressure pushing them. The electron I introduced on this side of the wire, is it the same as what comes out of this side of the wire? No. This wire is filled with, well, in this case, copper. Copper is a metal. It's filled, packed, jam-packed with electrons. Sort of like if I have a garden hose filled with water, if I put a drop on one end of the hose, is it the same drop that comes out the other end? Of course not. That drop merely pushed all the water in the hose along, and another drop came out. Electrons going through a wire are the same thing. I introduce an electron on this side, it pushes against all the other electrons, and another electron will pop out of this side. Okay, so that sort of makes sense. So if I stop pushing anywhere in that wire, I stop all of the electrons from flowing through it. All right, so let's talk about waterfalls. What? Let's talk about waterfalls for a second, because we have some things that are very much related to electricity, and you can imagine them in waterfalls. Imagine, if you will, you have a very tall waterfall. A very tall waterfall. And here is water flowing over it. Because the waterfall is so tall, each gallon of water has a lot of energy, right? If that gallon of water falls all the way down, its kinetic energy would be really high. If somebody drops a gallon of water on you from a quarter mile up, it's going to hurt. But could you stand under that waterfall and survive safely? Well, what if there's hardly any water coming down that waterfall? What if it's just a few drops falling that quarter mile? You'd be fine. You'd be absolutely fine. So you can have a very tall waterfall which imparts a lot of energy for each unit of water, or you could have, obviously, a much shorter waterfall where each unit of water has far less energy associated with it. The height of the waterfall is related to the electrical concept that we call voltage. Voltage is how much energy you've put into each chunk of electricity. Now, a chunk of electricity, instead of a gallon of water, we have a coulomb of charge. Remember that 6.25 times 10 to the 18th electrons? A lot of stuff, a lot of electrons. Each coulomb of charge, if you do 1 joule's worth of work on each coulomb of charge, you have a new unit. Okay? That new unit then is what we would call 1 volt. So 1 volt is 1 joule's worth of work per 1 coulomb worth of charge. What if I did 1 joule's worth of work on 1/10 of a coulomb? How much voltage have I increased it by? Well, 1 joule on 0.1 coulomb. You could do the math, or you could probably figure it out in your head. That would be 10 volts. If I do 1 joule on 2 coulombs of charge, well, that's only half a volt. So that's how you figure out how much voltage it is, and it's very akin to the height of a waterfall. How much energy does each gallon of water have coming over the waterfall? That's purely due to the height of the waterfall. But at the same moment, you realize that this is not what would make a waterfall lethal. It's part of it, but it's not the whole thing. A really tall waterfall with only a few drops is actually very similar to the Van de Graaff generator. That Van de Graaff generator in the back, that gives me something on the order of 400,000 volts of electricity. Now, if you only know a little bit about electricity, you know you better stay far away from 400,000 volts because it'll just smoke you. But we take the shocks from it all the time. Nice big shocks. It feels funny, but it doesn't really hurt. It's like being under a hugely tall waterfall where only a few drops are falling on you, right? So the voltage might be really high, but it's not doing very much to you. The doing stuff, you realize, in a waterfall has a lot to do with how much water is coming over the falls. Well, how about Niagara Falls? Nowhere near the tallest waterfall around. Could you stand under it and survive? I think not. That much water hitting you would do you so much damage. Even though each gallon doesn't have a huge amount of energy, there's so many gallons. So the other concept we have is the current. And the current is measured in amperes or amps. And 1 amp is equal to 1 coulomb of charge passing a point in 1 second. So if I have a coulomb of charge passing any point in a wire in 1 second, that's 1 amp's worth of current flow. Now, think about it. In a waterfall, how much that waterfall can do is going to be a product of how high it is and how much current it is, how much current is flowing over it. So if we think about this then, we come right up against something that you will find very useful being a homeowner someday, and that's the total power delivered is going to be volts times amps. I is the symbol for current. I don't know why. That must be why you use an I. So volts times amps gives you the total power. How do the units work out? Let's look at the units. A volt, again, is a joule per coulomb. An amp is a coulomb per second. You see what happens here? The coulombs cancel, and I end up with a joule per second. Back to the physics joke. Watt is a joule per second. Remember, the proper answer to this is yes. A joule per second is a watt. One joule per 1 second is 1 watt. So, if you go down to your basement and look at your circuit breakers, you might see a 20. That would be a typical thing written on the side of your circuit breakers. That means those are 20 amp circuit breakers. They can only handle a load of 20 coulombs per second. That's a lot of electricity. And say one bedroom would have one circuit breaker on it. A bathroom would have another circuit breaker. So each one of those can handle 20 amps of 20 coulombs per second of current. Well, standard house voltage is 120 volts. So if we look at this, power equals voltage times current. So if we have 120 volts, and your power, it may go between 110 and 120 volts, and electrical devices really don't care at all. It doesn't make any particular difference to them. 120 volts times a maximum of 20 amps, that equals 2,400 volt amps, which is what? 2,400 watts. So if you buy a hairdryer, you'll often see advertised right on the hairdryer, it's a 1,600 watt hairdryer. Ooh, well, that's useful. That's a lot of drying power. How come they don't make a 2,000 watt hairdryer, or 2,400 watt hairdryer? Heck, you could handle that. But could you turn on lights in that bathroom too? Well, no. If you're already running at 2,400 watts, you don't have any headroom. So if you have other devices on a circuit, in a bedroom or a bathroom or in the kitchen, if you have other devices on and your maximum is 2,400 watts, if you exceed that, what the circuit breaker will find is that its little element there is getting so hot that it trips the circuit breaker. It's a mechanical thing. At least they used to be mechanical things, and it would cause the circuit breaker to turn off. So 1,600 watts gives you 800 watts of headroom. So you can have a few lights on, maybe you can have the stereo on, a few other things, and you won't trip the circuit breaker. Nobody likes having their circuit breakers tripped. Question: if you're doing your hair, somebody else comes in and wants to do their hair with another hairdryer, will that work? Will two 1,600 watt hairdryers work on a typical house circuit? I'm afraid not. Right? 1,600 and 1,600, 3,200 watts significantly exceeds your 2,400 watt maximum on any house breaker. So that's the first go round on electrical circuits. They must be in a closed loop to flow. Your battery increases the voltage potential. In other words, how hard the electrons are trying to push against each other. You do not want to just put a piece of metal over a battery, because if those electrons just go from one to another, they'll dump all their energy right into that little piece of metal. That metal will get very hot. The electrons will flow way too fast for the battery's capacity. It will destroy the battery. It could cause a fire. It's why we use circuit breakers in the first place. If you should ever stick a fork in an outlet, you're going to cause fire. You're going to get electrocuted. There's all sorts of bad things that happen in that. The circuit breaker is meant to handle at least a few of those things. You're getting electrocuted. Yeah, sorry about that, but that might still happen. We have other circuitry, which we'll talk about later, to try to keep you alive if you should do really dumb things with electricity. Thanks. See you next time. Do you hear bells?